Okay, so for this question, what we're given is a magnitude plot and a phase plot of some signal, and we're also told that these manipulations happen to our input signal in the time domain. And then based on the modification to this input signal, we are to match what would happen in the magnitude and the phase response plots. So let's get started. Um, I have a list of properties here of what we're going to need to start. These two pieces right here are just numerical representations of the magnitude and the angle response. And then this is just a table of the properties that we are going to need to be able to do the question. So the first is going to be x of t convolved with itself. And if we look, we know the property of convolution, the one that we all like. Convolution in the time domain is the same thing as multiplying the signal in the Fourier transform. And so as far as the magnitude response goes, we can just look. So essentially, our total signal is going to be the magnitude multiplied by the phase. And so the total signal is going to be the magnitude squared, essentially, and the phase response squared. So the magnitude squared is going to be, omega plus 1 squared for omega is less than 0, and negative omega plus 1 squared for omega is greater than 0. And at 0, that's still going to equal 1, and it's going to have, that sort of quadratic response. So M3 is going to be our magnitude response for the convolution. And then as far as the phase response, it's just going to be, since it's the input signal convolved with itself in the Fourier transform, it's just going to be the angle response multiplied by itself, and two exponential functions multiplied together just add. So the angle response is going to be e to the negative j omega pi, because pi over 2 plus pi over 2 is pi, obviously. And that's going to leave us with the only angle response with a slope of pi is this one right here, a2. For the next one, x of t minus pi over 2, we just go and look at our table of properties. Right now we're looking for the time shift, f of t minus t naught. In this case, our t naught is that pi over 2. And notice that all we're doing is multiplying by an exponential function, so that's actually not going to affect our magnitude at all, because the exponential functions are just going to add. So as far as our magnitude, we are actually going to have the exact same magnitude response as our original signal did. And then for the angle, again, we're going to have the exponential function of pi over 2. Our shift was also pi over 2. Those pi over 2's are just going to add. And our angle response is going to be a2 again. For x of 2t, we go look at our table of properties again. We're looking at time scaling this time, f of at. And notice that we're going to get 1 over the magnitude of a times f of omega over a. So essentially, what we need to do is we need to go everywhere there's an omega in our current signal, we just need to divide by our a, which is 2. So our angle response is going to become e to the negative j omega over omega times pi over 4. And if we look through, the only thing that matches that is going to be a3, because that slope has now decreased to negative pi over 4. And then, if we look at our magnitude response, so this part is a little bit tricky. Our omega here is going to have an omega divided by a, which in this case is 2 under it, and then also the overall magnitude is going to be multiplied by 1/2. So that, remember that omega divided by 2, that's going to be a scaling, so it's going to scale it by a factor of 2. So instead of going from negative 1 to 1, we're now going to go from negative 2 to 2, and then that overall magnitude scaling is going to, kind of shrink the magnitude by a scale of 1/2. And so what is going to match that is going to be this plot right here, M4. Now for the last one, this one is actually a little bit tricky, and a little bit involved. I'm just going to gloss over it pretty quickly. So we have x squared of t, which is going to be essentially x of t multiplied by itself. And if we go look back at our table of properties, time domain function multiplication in the time domain is the same thing as convolution in the Fourier domain. And so let's start by looking at the magnitude response of this. And essentially what we can do is convolve the magnitude response with itself. And so we say we're going to flip that, and we're going to have another triangle, and then so we're going to have essentially a quadratic type function. When we convolve it, you can kind of imagine, another triangle moving across this, and then so your function will be a linear function times a linear function and integrated, which will be a quadratic of some sorts or a polynomial of some sorts. And it's also symmetric, so it's kind of going to go up and back down. And so the only thing that really makes sense in this scenario is M6. And as far as the angle response, that actually ends up being unchanged. And the only one that is unchanged is A1. And in order to prove that, it takes actually quite a bit of time. And if you read the lecture notes from the source, I found this in the link MIT. There's a pretty detailed solution to it. So I'm not going to get into it because that would make this a very, very long video. I hope the rest was helpful. Thank you.